nice arrangement. So Tulef is taking care of the first part, and then in the last half of the program, Tulef is going home, and now Kirsten and Sigurd Sannan and Jules Mellon are coming to take over for Tulef. Yeah. Okay, so please, Tulef.
Maybe I should start with acknowledging the people I've been working on this project. It's Alan Kirsten at Sandia National Lab in New York, and then it's Cecilia Shannon, who is at CTEC Energy Research in Trondheim, Norway. That's also the same place as I work now. There's interview on the presentation, and that's so this is sort of the draft on my defense presentation. So I was told to hold this presentation 1 hour ago, so I'm sorry for some unfinished stuff here. But I hope we can understand something. Just don't hesitate to ask questions. Okay, I jump over some first slides. I think I will start by talking about the standalone linear edge model. Some of you know a little bit about it, but I think it's good to have a background on that. And then I will continue with presenting the new model framework, which we call the LEM 3D. And first, in a simplified version with the constant density. Maybe we can look at some non-reacting test cases, but maybe more interestingly to also look into the non-constant density, the mixing reaction model. So why turbulent combustion modeling? Okay, we can skip this one. Some of the challenges in turbulent combustion modeling have you already discussed. One thing is that the small scale structures are very important, because that's where the reactions are mixed and the reactions occur. Turbulent stirring is by nature an advective transport phenomenon, but it's usually or often modeled as a diffusive process. So either in RANS, where you model the whole bulk transport as an additional mean diffusivity, or in LES where you resolve the larger scales, but the small scales you still treat with some kind of diffusive mixing or transport model. So the linear eddy model, contrary to the standard model, is based on a phenomenological description of turbulent stirring, so that's not directly from first principles. But the distinguished features of the model is that molecular mixing and chemical reactions, they are fully resolved in one dimension. So down to the Kolmogorov scales. And the turbulent stirring and the molecular diffusion is treated as separate processes. And essentially it resolves all relevant length scales in turbulent mixing. So some more details on the linear eddy model. It has basically two main components. The first is the one-dimensional mixing reaction equation for a general scalar, written as this.
What is a phi?
That's
one plane?
No, the phi is a general scalar. It can be temperature. It can be mass fraction of the species. Yeah. Or
This dm is molecular diffusion?
Yeah, so that's molecular diffusivity. And the last term is a source term, so chemical production or
don't have here flow. You don't have here advective tone.
No,
blah file.
no. In the model has no advective part in its basic form. So that's something you have to add to the model.
Oh, I see.
Yeah.
But this is supposed to be
But
calculated between mesh points, basically. This equation.
yeah, so this is implemented on a regular 1D domain.
But between mesh points in the 3D simulation mesh.
Yeah, well, I come to that. You can build different kinds of, or you can implement this model in different ways. So Serge Menon has his method for implementing this model in LES, and we have a different approach, which I'll present now, where we build a more structured model, and this is coupled to RAMs. This is the first model component. The other contains some advective part, and this is the turbulent stirring. And this turbulent stirring is implemented by so-called triplet maps, and I will explain what they are in the next slide. So imagine if we have a linear scalar gradient, which is this black and red line, and if we perform a triplet mapping on a section of that gradient on that domain, we do the following. We create 3 copies of a section of the scalar field, like this, and then we compress the copies by a factor 3. We triple the gradient, and then we invert the middle copy, and of course put it back again on the domain. And by this we have a conservative mapping. It conserves the property that we have, and it's also continuous.
So in such a way you model velocity field, which contains several components like rotation, shift, and others. Yeah? And they're independent random processes or what?
In this way, you model the turbulent flow. Of course, not the large geometry dependent structures, but yeah, what is in the inertial range and below is modeled by.
But these ingredients like rotation, like shift, they're independent each other, or how many random quantities do you have here?
Oh,
This is for a scalar only, no?
yeah, this is for a scalar only. Yes. Yeah.
For the number density.
Or whatever it is. A scalar. So what the idea is primarily is to increase the scale.
Yeah. Yeah. So the physical interpretation.
Increase the distance between the 2 points.
Yes. So no. So you have so shear layer is not infinitely thin, but it's thicker, and you adjust it to what you want in a conservative manner.
Yeah. Yeah. Maybe. Yeah. Yeah. So it emulates the compressive strain and the increase in scalar interfaces caused by 3-dimensional turbulent eddies. That's the idea. And this is
Physically, you have some history effects. In what way?
yes.
The history effect
So in the linear eddy model, there is no direct history effect. There is a version of the model called the one-dimensional turbulence model, where you also have the
you
velocity.
change, you do this triplet.
Yes.
With some frequency.
Yes.
What is the frequency?
But the frequency is dependent on the turbulent diffusivity and also the distribution of the eddies of the turbulence spectrum.
I guess you're going to explain that or not later.
Yes, I will go in some details.
Yeah, so therefore, please continue, I guess. So,
we wait.
I think
okay.
it's better to wait.
I can't guarantee that I will. So numerically, so this is implemented as a permutation of fluid cells, and in this sense, this is a non-diffusive process. So in this way, you don't mix or you don't do any diffusion by the turbulent stirring. So this is just to show you how this is done in practice. Let's say that you have your 1D domain. This is the timeline. You start with some initial field. The next thing you do, you sample the time for the next triplet map, the stirring event. And this is, you sample this from a Poisson distribution. And the rate in that distribution is dependent on the turbulent diffusivity and also the distribution of the eddy sizes.
The turbulent diffusivity depends on scales of eddies. Or
Yes,
you
so
speak about the turbulent diffusivity in the maximum scale of turbulent motion.
Yeah, I speak on the overall.
It's not framework, no?
Yeah, in a round frame.
So you have to diffusivity and you have the integral landscape.
Yes.
That gives you time scale. Or am I wrong?
Yeah, not simply that, because you have a distribution of eddies. So you have, when you derive it, you have to take.
So look at the mean or what?
Yeah. Well, I'm
No,
not
we should
sure.
see. Maybe
Yeah.
But you assume here a Kolmogorov scaling, right?
Yeah.
So that's how you find distribution between the eddies. Assume that you have a Kolmogorov scaling, and then you know how many eddies you will have at different scales.
And in what sense it is introduced here on a Kolmogorov scale?
It's by, I mean,
What?
you have the turbulence in intensity, which tells you the level here, and then you.
Well, it's been Kolmogorov spectrum, but how it's realized here?
Well, we'll be coming, right?
Well,
let's wait.
Well, maybe I should just because I haven't put many equations in this presentation,
Okay.
but I can, if you don't mind, I could just a second. Yeah. Some more. So this is a event frequency parameter, and this has a unit 1/second per second and length of the domain. And this is the integral scale. This is the Kolmogorov scale, and this is the Rand's turbulence diffusivity, and this is derived from you assume your scaling and so forth. Okay, so what you do is you sample the time for the triplet map. You evolve the mixing reaction equation to that time. And then you sample the length of the triplet map from a distribution which resembles this. And if this diffusivity is uniformly distributed, you just sample the position at where the triplet map should be implemented from a uniform distribution. And then you repeat this and you run this as a Monte Carlo or a stochastic simulation. And then I can back in the other presentation.
Just one quick question here.
Yes,
Just before.
sure.
But so you choose independently the time of stealing.
Pardon?
You choose independently the time of stealing. So there is no correlation between events. The events are chosen
Yeah, no, this.
randomly without any correlation in time.
No, there's no correlation in time between them. That's right.
But it's not physically correct.
No, this is technically in time velocity.
Yeah, but
You can. Yeah.
This model.
But for me, if you modelize correlation in space with Kolmogorov, so it's practically the same time scale in time. So it's yes.
Okay.
Yes.
The framework of crashing model,
Yeah, but
you can do it.
but
Of course, this is synthetic velocity.
it's an age, it's not
Yeah,
law.
of course.
It's
Yeah, I agree with you.
So
Nonetheless,
There's no correlation. It's like
Yeah.
that. Okay.
I can make a
White noise.
comment. There is a, as I said, there is another version of the linear eddy model called one-dimensional turbulence, and then in that model you carry also the velocity field, and in that model you have some history effects. There you will have
So some correlation with that.
yes.
Okay.
Yeah. So, but I'm not an expert on that model, so I will encourage you to say the questions to Alan when he arrives.
in the limit of the, if you play on number, you would see that you get altogether it's the dt divided by lk cube. So if you look at L is much bigger than lk, then you get altogether. So it means that the model is based on the Kolmogorov length scale only. On one hand, and then you have eddy diffusivity on the other hand. It sounds like putting two animals which are of this different origin together. So any explanation for that?
introduce two scales.
Yeah, I know.
One is
A small scale for
L
length.
small is length
Length.
between.
Yeah. No, but I mean, if you look at the limiting case.
Yeah, limited case. Yes.
So it means I don't see why how you can mix the two concepts together in this way. So I mean, the limiting case. Well, maybe
I'm not
we
sure if I can answer that.
next week we can continue discussions.
I'll make you Alan Tessin. You can ask about Alan Tessin.
Yeah, sure. Sure.
But,
It's coming. So.
Okay, so okay, I have this slide just as a demonstration. I run a mixing of a point source. So it's 1D domain, and then at t equals t0, I have a point source, and then I see how this spreads out, how the model spreads this point source. And you can see that you have different events at different time or of different sizes. And you see the effect of molecular diffusivity, how it smooths these events out. And
In the equation there is a source term.
yeah, okay, the source term is not present here.
Zero.
No,
Okay.
zero. No,
Just diffusion.
yes, no source
But
term.
it's just not because no molecular diffusivity coming in. No molecular diffusivity.
Molecular diffusivity is
Is included.
yes, it's included.
Where? In which part of the equation? Because it was not in the time. It was the original equation you made.
The mixing equation.
The mixing equation. Okay.
Yeah,
I guess.
it was.
The very first equation.
Yeah, this is
X1.
okay. Okay.
The index.
Yeah, that's okay. So
What is strange is this picture. In fact, in reality, we have some even for isotopic turbulence, the mean velocity is equal to 0, we have some advection effects. So it's not only this, but also some movement from right to left, and there are no movement.
Yeah. Here mean velocity equals 0.
Yes, even velocity.
Mean velocity equals 0.
No, even mean velocity is equal to 0. There are
There are
some.
fluctuations. But
Yeah,
It is
not like that. We have the fluctuation from left to right.
I guess,
So-
but I guess something can.
This is evolution of mean field. This is evolution of mean number density,
No,
for
it's
example.
not mean field, it's instantaneous field.
Yeah, it can be interpreted like.
Yeah, but so there no this element.
In your test case,
Yeah.
how does the root mean square value evolves with time? Do you have, what kind of process do you have? Do you have a t to the third second? You see, like a turbulent diffusion, turbulent diffusion. You know,
Yes.
you know the
Yes, well, I haven't studied that in particular, but there is a paper where he
But you
he
have
looks at heat spreading of heat from point source from line sources, and he gets some initial scaling that you have in the what's it called, the turbulent. You have the turbulent convective range first, where it scales like how is that here? The sigma goes like
in this time like T.
like T, yeah.
Yeah.
Yeah, and then
later like the square root of T.
Square root of t.
and then it goes like the square root of T. Yes. So it has been able to reproduce
quite well with,
So-
with
some-
this modeling.
something similar. There are some artifacts here.
You need
Yeah.
to tune the parameters.
Some tuning, of course. But of course, there is one artifact with the model, and that is, of course, turbulence is a continuous process in time. But the turbulent or the triplet maps, they are instantaneous. So and that, of course, is not.
You're lacking a time scale for that.
You're like, yeah. So that produces some artificial effects, especially close to a source.
But this is just one scale flow.
And this is just homogeneous turbulence, one scalar starting as a point source.
The condition is not clear for me. What I say, for example, from very beginning, you have a very thin mixing layer, okay? And this mixing layer is converted by the other vortices. So the picture is not like that. You see that what I...
In the equation, he doesn't have term u, nabla,
Here,
phi.
so, but we have to modelize this.
Yeah, of course. So this is usual diffusion, that's it. Usual diffusion with a
Yes.
given velocity.
I understand that,
Yeah,
but if you don't describe this moving, so
Yeah.
what is in general case what we have? I ask him and not you, because he presents the model, the idea. I want to understand what is behind of this idea. Okay, without interpretation.
Yeah, okay.
Okay, we can speak after. Okay, but not because for me it's not clear. Maybe you have some explanation. You saw the shimmer, okay?
Yeah.
And from very beginning, it's seen every day.
Yeah.
Why we don't see here? What is missing?
Well, I'll be careful to interpret, give too much interpretation from this simple test case. But of course, one thing you set in this model is the integral scale. That's something you give as an input, and the behavior will, of course, be dependent on that. And what we see here is not from t equals t0, and it's from t equals some time larger than t0. So you don't see the initial.
Do you
But,
have this information? Do you have this information? From very beginning.
Yeah, I think I can.
When you
Not right here now.
No, not now.
But,
But this model, in fact, models this flapping. So it's this sigma goes as t. So that is a flapping or meandering process. So it gives that.
But where? At the moment.
Yeah, you can see it. That was the result of the model that he just explains. Sigma goes as t at first.
But
So that is exactly this meandering that it's modeled now. And then later it goes like a turbulent diffusion process.
yes, of course, but I can't
So
see
it
here.
is modeled. And you can see this probably as kind of
Okay, so
as a mean of many kind of.
yeah, so another important point also is that this is not a DNS. This is a stochastic representation of
Yes.
what the turbulence does. So we should probably not look at this and expect to see what we
But
see in nature.
if you don't reproduce this flapping,
Well, you should,
Well, it
you
does.
should reproduce the statistics
Of the
that's-
flapping process,
that's the
yes.
point. Like we. Yeah. Okay. So here I claim standalone LEM. It works well for simple combustion applications. There are several papers on that. It has some limitations, and one is that large-scale geometry-dependent flow structures they need special adaptations. You need to do some tweaking, and as a result of that, a linear eddy model in standalone 1D mode is limited to rather simple flows. And as we already talked about, a linear eddy model contains information about the scalar field only. So flow field information must be provided for some work.
So I'm not exactly sure what you mean by standalone.
Yeah, good question. Standalone is contrary to what I will present. The 3D where we couple several.
So standalone means you're actually solving really just a one-dimensional problem.
Yes,
And
that's
then
the
there's-
standalone.
And then what is
I
it?
agree that it's a bit confusing.
And then what is the? Is there any particular scale where you have at this point some difference between the full equations and the LEM equations, which are of course not the full equations?
No.
Is there do you resolve the full equation a lot within scales?
Yeah, yes.
So how many mesh points do you have then on? I mean, where's the cutoff in scale?
Okay. Well, I think I should proceed. I'm not.
So then I misunderstand this, of course.
Yeah.
I mean, I understood that you sort of have a one-dimensional model,
Yeah.
and then you have a reasonably coarse-grained mesh on which you solve the full equation, this advection term. And then on smaller length scale,
Okay,
you will have
no, it's not exactly like that. It's so I think I will just proceed and then you can see if I manage to answer your question. Okay, this is more background thing. So the aim of our work has been to extend the capabilities of this standalone linear eddy model to model more advanced geometries and more advanced problems. And we have had sort of a guideline for this, and this is that we wanted to maintain the strict distinction between the mixing and the turbulent stirring, which is inherent to linear eddy model. So we would try to avoid for example, implement the mean flow or the mean flow advection in a diffusive way. This has implication for the mean flow advection, and also when we have some chemical reactions to the dilatations from heat release expansion. So, okay, this is how the model is constructed. This is a single standalone linear eddy domain, and it's discretized in a number of wafer-shaped control volumes, wafer-shaped like this. Yes.
Just,
Are you?
I think I know what standalone means, but
Yes.
I just want to verify. You mean by standalone, you mean that you get the velocity field from somewhere, and use it in your LEM standalone model, but you don't feed anything back, right?
Oh, maybe I should omit. Maybe I should omit the standalone expression. It confuses. But what I mean here is, it's just the 1D model as I have presented it, opposed to the 3D model that I'm gonna show now. Yeah. So, but that's good feedback. So, thank you. So, and then further, a number of such parallel LM domains are then bundled together in a stack, and then we resolve the whole domain of interest in one direction. Let's say the x direction. And similarly, we construct we resolve domains in the y and the z direction in the same way. And where the domains intersect, we define a supergrid of 3D series are defined. So, yeah.
What is it, supergrid?
Yeah, well, so if this is the grid that resolves the 1D domains, the supergrid is a grid larger than the small or the fine resolution, and this is the cubes that you can see here.
And these cubes are the points where you have the mean things, right?
Yes.
Between velocity and thermal diffusion.
Yes.
Right.
How they intersect? It's in virtual sense. It's not real.
No, it's in real. Yeah.
So
That's really how the model is constructed.
So one small cube models small-scale processes, and all this ensemble of cubes can model large-scale processes.
No,
Or what?
well, the mean flow.
Yeah.
So is set by fluxes on each of the faces of these 3D CVs, and then the small scale processes they go on the 1D domains, but it's not they are not limited to just go on inside of the 3D CV, but they generally go on a scale smaller than the discrete scale.
But I have some question. I understand how you can calculate at the same time in 3 directions, in x, y, and z, with the 3 planes. Because
Yeah,
there
well,
are some intersections. So how
Yeah, you can.
how do you do that?
Yeah, they are. You can say now that these 3.
The intersection.
Yeah, with intersections, they are 3 representations of the same domain. So we have, in the 3 directions we have 3 representations
So
of the
you
same.
do that 3 times independently
Yes.
for each direction.
Yes, and
So-
then we have some coupling, which I will come to.
It's not a real intersection. It's a virtual one. It's not a real intersection.
Depends what you mean by
Because
real.
your triplets are independent in each direction.
Yes.
It's
Yeah.
like that.
Yes, they are. Well, yeah. Sort of in.
When you draw, what do you do? Yeah. You have 3 directions.
Yes.
In each direction you do triplet.
Yes.
And how you combine them?
Yeah. Yeah. Okay. Then I.
It's not It's not clear from this screen.
So, okay, this is details about how the mean flow advection is implemented. Okay, so without the three domains, you can say that you have resolution in the three directions. They are not coupled by themselves.
Not coupled.
Not coupled. But to introduce coupling, we need coupling between the directions. We do, and again I will say this is it's a stochastic model, so it's not.
But how?
And then we do a rotation of the these 3D series, and then you have 6 different options for rotation. So in that way, you couple the different directions.
Some animation maybe.
Yeah.
So, why do you say 6? First of all, you have 3 directions, but altogether with nearest neighbors in the box, you have 26 directions. So why do you say 6?
Well, you have 3 axes.
Yes.
And for rotation, you can either and you have 2 directions. That you can see. Yeah. So that's.
But okay, you combine 6 fields.
No, you combine 3 fields.
But they are different for.
Yeah. So so if you have let's say in 2D, you have processes going on here in this domain, and then you do a rotation of this 3D CD, and then what was on this domain is transferred to this domain, but only for this 3D CD. So of course you will have on the boundaries here you will have some discontinuities that you introduce. But,
the initial condition for scalar field is the same, or because you calculate scalar field for each I don't know, for each triplet. You need the initial conditions for each direction.
The initial condition can, for example, be on, if you have something like this, the initial condition can be something on this domain. And by the LEM processes, the triplet maps and the molecular diffusion, and the rotation, you will have this scalar spread to all domains. So,
my question.
Yeah.
You do first triplet, okay? You obtain some scalar field. After you continue, do the second triplet. What conditions for scalar you take for the second triplet?
Well, you just evolve the same. Yeah, you continue to evolve the same the same scalar field. Yeah. Okay.
So it's not combination. It's the same condition.
No, it's just evolution of the field. So, okay, so I can try to summarize the non-reacting LEM 3D concept. So on each LEM domain, you have the turbulent advection and the molecular mixing, and then we have the structure, the LEM 3D structure, where we perform the mean flow advection of scalars, and we also have this rotational coupling of domains. And to have this going, we need as input a mean flow field and also a mean turbulence diffusivity field. So a mean flow field to affect the scalar and the mean turbulence diffusivity to drive the processes on the domains here. And this is so in general can be provided by by different other models like RANS, LES, or even from measurement data if you have a stationary problem or DNS. That's the non-reacting concept. Okay, so I'm not sure if I should go in. Okay, I don't think I will go in detail on all the results. Of course, I spent a lot of my PhD on investigating different properties, what's working and not, and especially these rotations, of course, which is something something new, and so
Okay. Here you have two random processes. One can model molecular diffusion, just Brownian diffusion. Additional random process is random velocity field, which can give you turbulent diffusivity and transport coefficients, in principle, in this system.
So
Here you describe two processes.
yes,
One is a Brownian diffusion,
yes,
which is
yeah.
trivial random processes, which all Wiener process can describe. Maybe you describe in a similar way. But also you have turbulent flow.
Yes.
And turbulent flow can give you turbulent diffusivity. And also it can give you mean flow.
Yes.
If you average of this
Yes.
field.
If you average.
Yeah.
So you wonder what the
So, but you have also additional information about mean flow from LIS, RANS, and data.
Yes.
What does it mean?
It means that you get also the average mean flow and the average turbulence diffusivity that you need to drive your models, which give you the small scale behavior.
Yeah. But in principle here, velocity field is a given.
Yeah.
Okay.
In principle, it's given,
Yeah.
and also the average turbulence diffusivity field is also given. Yes.
Okay.
So, I think I will just go to to show the principal idea behind when we extend the model to reacting applications, because then in addition on each LEM domain we will have chemical reactions, and these chemical reactions they have some resulting heat release and dilatations, and they are taken care of on the more on the LEM 3D level, and of course these altogether result in a density field which feeds back to the flow solver. So this means that the whole model must be run with some kind of iteration in between. In our case, it's for the moment only RANS. So you need some kind of iteration loop to reach steady state.
Your runs is semi-compressible, I suppose.
It's
Otherwise you get temperature.
incompressible.
Oh, okay, semi. That's a function of only temperature,
Yeah,
not pressure.
that was pressure correction. So I'm not sure if I will go into more detail on this now. Of course, we can discuss more.
So with reaction, you use the same triplet.
Yes, those processes are basically the same. In addition, you have some kind of dilatations.
So there are no effect
expansion.
of dilatation of the triplet. Triplet is chosen as
Yes, no direct effect.
not.
Yeah, it's an indirect effect because the mean density field will probably affect your mean turbulence diffusivity field. But that effect is
But it depends on, for example, mass moving parameter. It depends on. You have here in some sense two-phase flow. You have fluid flow and you have particles or passive field. So
Yes.
there is back reaction of passive field or this is scalar field to the flow only if, for example, if you have particle density of special density of particles of the order of fluid density. So in other words, if a lot of particles, they can affect to the fluid flow. If you have small number of particles, this is like a passive scalar.
maybe
But you introduced back reaction
yes.
of the mean density.
Yes.
This is density of what? Fluid density or?
It's fluid density.
This is fluid density.
Yes. Yeah. And so because it's these wafers of these cells, they contain a certain amount of mass, so they are like fluid cells, but you can say that.
But you have continuity equation for the fluid.
Yeah, but the point is that as it heats up, it will take more space, right? And then it creates more lens cells, right?
Yes.
So you kind of introduce more lens cells here all the time, which make the whole thing expand. So it's continuous. You conserve mass, but not volume. So that's basically what it means. So when you increase the volume, you feed that back to around some time.
But there is question for triplet, because if we have some compressibility effect, we have some change of the velocity triplet.
Yes.
It's imagine, it's clear, even you, for example, you know the mean velocity, mean density change, okay? So we can suppose that triplet is the same now in the same direction, dependent now.
Yeah.
Because it depends how the QTD is structured.
Yes,
In this
and
case.
with this model, it's
But
the coupling is very indirect.
but triplet is in each direction is the same.
Well, it's
The same.
principally it's the same. It's you know, it's governed by the mean turbulence diffusivity field. So, but in principle it's the same. Yes.
Can you deal with differential diffusion?
Yeah, absolutely.
Absolutely.
And that's one of the things that's really straightforward here,
Okay.
because we can
We can change the coefficient.
just change coefficient and then you have it. So both molecular diffusion and chemical
Reactions.
reactions are easily implemented exactly.
What do you get now for the scalar dissipation rate? What gives the living edit model now? What kind of PDF, for instance, does it give them?
Yeah, I haven't.
Because that is already important, of course, for total combustion.
Yes, I agree. Can't remember right now, but there are some papers where the scalar dissipation spectrum, or the scalar spectrum has been computed I haven't done that myself. But, so of course that's very interesting to see the linear edit model does one thing and has some features, but now when we put it in this type of structure, what do we lose? I think that's an interesting question. I know that these rotations, they will slightly influence the mean dispersion. It increases the mean dispersion by some factor, but it also gives some additional mixing. So the RMS values, for example, are lower for corresponding LAN 3D to LAN 1D case. So again, it's a quite novel concept, and there's still things to work out.
And are people putting in anisotropy in this linear edit model? So that depends on the direction.
I guess, well, it should be possible to.
Some often you have that in reality, so that it's mixing fast in one direction and in all directions.
Yes. Well, it's as it is constructed, that the triplet maps depend on the mean turbulence diffusivity. So if that's anisotropic, the mixing subgroup mixing process will also be anisotropic.
Yeah, okay, but then you have to be very careful with rotation in the end. If you couple the three directions together.
Yeah, probably. Yeah. So.
Okay, are there any more questions?
How about validation of this compared to this direct simulations? What is the status on that?
That's actually still on the list. We have run some validation with an experiment. Too many slides. Okay, so this is the points here are the experiments, and the case is here maybe you have why not just show the slide? Okay, this is the setup. You have air coming from you have an air jet, and in the self-similar part of the velocity field, you place a point source. This is the measurement of the Warhaft and Tom, and then what we see in the this is the specification of it. Is 30 millimeter, 9 meters per second. The Reynolds number is 18,000.
So just, I mean, from the previous curve, you saw then have some agreement, yeah?
Yes. So
here, some.
So what I've done here is to run the LEM 3D with the velocity field and the turbulence diffusivity field input from the experiment.
Yes.
And here I've run with different integral scales.
You mean cutoff scales or what?
No, the large scale. The large scale. That's an input to the linear model. So,
right. Yeah. But the.
Yeah. So.
What do you mean? I mean, by large scale, you mean the small scale as far as the large scale model is concerned. What do you mean by that?
So that's the largest eddies, right?
It's
large interval.
yeah, it's basically the largest eddies. But yeah.
I mean, do I still understand correctly that you have a large simulation and you use this LEM as a separate scale model? Is that right?
Yes. But
And so then the question would be: is the resolution of the large scale model, the coarse-grained model, are you changing that, and are you showing us how that converges, or what are you doing or showing us here?
no, I use the same grid. So the only thing I change here is the integral scale as an input.
But the integral scale should really be the same, of course, because you have run the same physics to model here.
Yes. Yeah, maybe you're right to that. But, yeah.
I think what you in fact specify is in the ratio of the source size and the integral size. Because then initially you get again this kind of flapping process, so that sigma goes as t, and then after some time you get the thermal diffusion process. So, and that depends of course on this ratio or not. That is more or less what you show here.
Yes. Yeah.
So in fact, you first have sigma is t behavior. Depending on this ratio, it takes a longer time or a shorter time, and then later you get the thermal diffusion process.
Yes. Yeah, that's it's partly correct. There are some model artifacts also here.
Yeah. Okay.
Could you give more details? What the curves
so
what different parameters for these curves? There are 4 curves.
Yeah, there's 4 curves.
Even more. What
That's
is
great.
the difference?
This is yeah. So I've run this with.
And otherwise, it's not clear. What do you compare with what?
I agree. It's 4 different model integral scales or integral scales.
4 scales. 4 internal scales.
4 different.
Okay.
So just to as a parameter study to investigate the difference.
And
In
now
one
what
way,
is,
Axel is right. I shouldn't. It's one physical problem, so maybe I shouldn't
and now
change this. But in
what
fact,
is the difference of curves?
yeah. And then we go back to the curves.
Yes.
And this is 114.
Yes.
And that's half that. And that's 56. And that's 28. And that's 14.
So we can conclude that the flapping is not taken in account in your model. So this is a link with the flapping. Why?
Here, you change only rewards now.
No, it changed interval scale.
Yeah, so and Kolmogorov scale is fixed.
Yes.
So in some
Yes.
sense, he changed rewards now.
Bigger interval scale,
Yeah.
more important flapping. Okay. Okay.
Mm-hmm.
So maybe it's not so important for for fish, but for us, for example, if you live nearby of one chimney with a pollution, you can die. Yeah? If you calculate like that, you can die. You agree or not?
But I mean, this only shows that it's
No.
the integral scale of the experiment
The
is
problem.
not set, right?
I explain what I mean here. In fact. Because when you have a very big interval scale in comparison with a diameter of a jet, you will have from very beginning
Right,
flapping.
exactly. But in this experiment, it probably was not a big integral
Yes,
scale.
yes.
So we don't know if it works or not,
Yes.
because it was a different comparison.
If I look at the experimental data, I saw that integral scale is much bigger than this one. Okay?
You saw that?
Yes, I saw that. I have experience with jet, so I saw that. And what does it mean in fact? Because if you put, for example, here some captain, some zone, okay? If there are no flapping, it will be the diffusion scene. Okay? The PDF will be very close to the Gaussian curve. Okay? But with flattening, you will have two peaks. Something, nothing, or per guess from jet. Okay? So it's quite different. PDF.
I see that, but does anyone see how you
And
know
what
that?
I see from these curves, that if the integral scale is very small, it's okay. They are not taken. The scale is growing, you have the flattening. So the model doesn't describe this physical phenomenon.
Oh, but in the experiment had the same integral scale always.
Yeah. No.
Yeah.
No.
Well, I guess in reality the integral scale grows somewhat with
you have forced integral scales.
Just for as a parameter study, because yes, and I mean this one is probably not realistic to include, but what is it reported if I have it here? Okay, you see what the experimentalists they report as their integral scale is 28 millimeter, and that is taken as the half width of the jet at where the point source is inserted.
They measure integral scale of turbulence? In
Well,
this experiment,
the way that they have
they
measured,
measure this or not?
the way they measure it
Yeah.
is by taking the half width of the velocity field at the point where the point source is inserted. So and this is the integral scale. Maybe this is not correct.
Usually in these experiments, when you would like to measure integral scale, you calculate, you have velocity field, measure velocity field, and you measure and you calculate 2-point correlation functions of the velocity.
Yes,
And these 2-point correlation functions allows you to measure, to determine from experiment integral scale of T.
yeah, they haven't done
That's
it.
it.
Yeah, I agree. But they haven't done it
And
in
very
that
often-
rigorous way.
Yeah, very often people use as an integral scale even just nozzle size,
Yes.
which is of course not always correct, but
Yeah, but in the jet it is proportional to the half.
Yes, of course, it change by the way.
of course a change with a distance, of course.
So it makes sense.
And
to
also,
take or at
turbulence-
least fraction of it.
Turbulence usually exists far from the nozzle, not close, and so. But usually correlation
But we
length
have
is
to-
determined only by the.
But we have to compare integral scale with a diameter, not of jet, but very small.
With this region.
Of course, not with jet. It's not important. We have to compare integral scale in this section with this type.
And what this comparison can give you? So,
The effect of flattening.
so it means that the scale of this structure
It's very
or can be larger or smaller than the integral scale of turbulence.
For example, if you look some shimming,
Yeah.
okay, from very beginning, if you nearby of shimming, sometimes you have nothing here at this point, okay? Sometimes something from the jet,
Yeah.
okay? And if you measure mean value, you can tell, oh, it's possible to live
The mean value of what?
mean value of concentration
Concentration.
from the jet. Okay?
Mhm.
And if mean concentration is good for life, you can live. But in reality, you have sometimes very large spikes of concentration. One day, for example, and you will die. Even the mean concentration is big. So to compare just one characteristic, mean value is not sufficient for this. This model is very complicated, okay? And it's strange to compare just one parameter.
Okay, we have.
Okay.
Yeah. Well, I
So
just.
you
yeah, I
have,
agree.
you have, for example, calculate the PDF of concentration and to show us if there are spikes or not, because this information is very important from an ecological point of view. Okay?
Yeah.
Because if you Do you understand what I want to say?
Yes.
Because if you give us just mean value, it's not important, because in reality, if I am not far from the chimney, I will have like that. Sometimes nothing, sometimes spike, nothing, spike, okay? And I will die during this period, simply. But mean value is okay.
I agree.
Our government will give us this information and tell, okay, we can live. It's not dangerous.
Yeah.
Okay. For me, this is the value of the modelization, to give information which can support us. Huh?
But we have compared not only the mean values. I've also looked at the RMS, but
PDF.
Unfortunately not the PDF. So that's on the two. Yeah, I agree.
PDF of concentration.
Yeah, because the model is very. I repeat, the model is very complex. Okay?
Yeah, so,
but the information which is shown to us very simple. I am sure that we can calculate these results with very simple model directly. Okay.
Yeah.
So, what is the value of this model? Okay. It's not to criticize the model. You understand?
Yes.
The results you presented. I don't understand really the details of the model. It's quite complicated. Really. But results.
But what's the nature of turbulence? Some kinds of dynamic instabilities of this jet.
In jet.
So it means that not in all situations should the same orders as the noise should be changed from place to place and not proportional. It doesn't seem like it should be proportional. Scale of energy contains scale.
No, but idea is that for this kind of, because I know very well this kind of experiments. This kind of experiment is done for ecological problems. Okay? Because in atmosphere, every time it depends where we are. Okay? What scale of vortices around our chimney.
It's another story. You mean there is some turbulence, and
which is given.
Given, not somehow.
Which is given.
So preturbulized media.
Yeah.
And we push in this media jet.
And there are some
jets with another turbulence.
And you have some
and
central station, for example, which is chimney. Okay? And we want to know, can we live or not? We will die or not?
We will die.
The question is very simple. But the answer is very complex.
The answer is very dangerous.
So you speak about the formation of homogeneous layers, and of course this homogeneities depends on turbulent parameters and
integral scale.
Yeah.
There are no mechanisms for turbulence.
Yeah.
Okay. Okay, very good. I'm sure we will have much more discussions on LLM later. I think we should thank Tony for his introduction.
And maybe one short announcement. If people are coming in over the weekend, please remember that that you have to dial the code on the entrance as usual. The code number is, maybe I should close the camera.
Yeah.